I want you to imagine a 400-pound four-wheel drive truck, and it is just absolutely barreling down a highway,
Oh, man.
right? It's moving at top speed, and it is flattening literally everything in its path.
Yeah, taking no prisoners.
Exactly. And that truck, for our purposes today, is the current wave of artificial intelligence. It's this automation just sweeping across the entire software engineering landscape.
Flattening all the traditional workflows. Yeah.
Exactly. But now, I want you to picture something else, standing right in the middle of that very same road, like directly in the path of this giant behemoth, is this tiny 40-year-old, almost entirely forgotten programming language.
Just standing there.
Just standing there. And you'd expect it to get instantly obliterated, right?
Of course.
But instead, the truck just drives right around it.
It completely ignores it.
Yes. So today, we are doing a deep dive into some truly fascinating recent research, alongside this really sharp analytical dialogue we have from tech commentators Jack and Jill.
Which is such a great source, by the way.
It really is.
Mm.
They argue that this obscure language, which is called Forth, by the way, it actually holds the blueprint for professional survival in the age of AI.
It's wild to think about a 40-year-old language being the key to surviving AI.
Right. And our mission today is to understand exactly why this obscure language acts as this impenetrable moat against the AI automation that is currently just devouring mainstream software engineering jobs.
Yeah, and the reason the truck trots around it, it isn't because Forth is some hyper-advanced, mathematically complex alien technology.
Right. It's not from the future.
No, it's actually the exact opposite. Forth survives because its fundamental architecture is just entirely incompatible with the way modern large language models, or LLMs, are built to consume and generate software.
It's like they speak completely different languages, literally.
Exactly. AI systems are designed to automate these vast procedural pipelines. And Forth, by its very nature, it just refuses to be pipelined.
Okay, let's really unpack this, because I want to get into the weeds of how live interaction with physical hardware actually functions.
Oh yeah, the hardware side is crucial here.
Because even if you, listening right now, know absolutely nothing about embedded systems, I promise this is going to be such an accessible and mind-expanding ride.
It really changes how you view coding.
It does. But to understand why Forth survived, we actually have to look at the casualty first. We have to look at what the AI truck actually hit.
The deer in the headlights.
Yes, the deer in the headlights. For the last 4 decades, the embedded hardware world, so the software running your anti-lock brakes or, industrial robotics, avionics.
The microwave.
Right, your microwave. That world has been completely dominated by the C programming language.
Oh, absolutely. C is the bedrock. I mean, it is the lingua franca of embedded systems.
But something is changing, right?
Yeah, what Jack and Jill's analysis really highlights is this massive shift occurring right now in corporate engineering departments.
Right.
Like, massive C development teams are being quietly disbanded.
Or severely downsized, yeah.
Exactly. Corporations are looking at these sprawling legacy C projects, and they're just handing them over to AI agents. And the cost savings for them are staggering.
Which is terrifying for a lot of developers. So let's map out exactly why C is so vulnerable to this.
Let's do it.
If you look at the traditional workflow of an embedded C programmer, it relies entirely on this process called batch compilation.
Right, the batch cycle.
Right. So a human engineer writes a block of code, they run it through a compiler and a linker, which generates this massive monolithic binary file.
A giant chunk of machine code.
Yeah. And then they flash that binary over a debug interface directly into the microcontroller's memory.
Yeah.
Then they reset the board, and they just observe what happens.
And something always breaks.
Always. When it inevitably breaks, they have to go all the way back to the text editor, tweak the code, and start that entire grinding cycle all over again.
It's exhausting. And that cycle text in, binary out, test, repeat, it is a purely deterministic, highly structured loop.
And that's exactly what AI loves.
Precisely. That is precisely the domain where an LLM thrives. You have to remember, large language models are, at their core, just sophisticated next token predictors.
You're guessing the next word.
Right. And they are trained on the entirety of GitHub and, decades of open source C repositories.
So they've seen every C function a million times.
Exactly. So when you ask an AI to write a C function to let's say, initialize an SPI peripheral on an STM32 microcontroller.
A very standard task.
Super standard. The AI doesn't need to understand the physics of the board to do that. It just accesses the statistical probability of what that C code should look like, generates the text, and feeds it into the automated build pipeline.
So it's essentially a factory floor.
Totally.
Think about it like, okay, imagine writing a long, complex letter to someone overseas.
Okay, I like this analogy.
You write the whole thing out, you put it in an envelope, you mail it, and you wait weeks to see if they understood it. And then they write back and say, hey, you used the wrong word on page 4.
You have to rewrite the whole thing.
Exactly. You have to start over.
Yep.
Or, writing in C is like drafting a massive, highly detailed blueprint for a skyscraper.
Right.
You draw up the plans in total isolation. You hand them off to a construction crew, which in this case is the compiler, and you just wait for them to build it.
And if a doorway is 2 inches too narrow?
You can't just nudge the wall. You have to go all the way back to the drafting table, redraw the blueprint, and send it through the entire approval process again.
Which takes forever.
It does. And because that process is so decoupled from the final physical product, an AI can take over that drafting table flawlessly.
Oh, easily. It can churn out blueprints 1,000,000 times faster than a human.
So C was basically asking for it.
Well, the vulnerability stems from the architecture of the workflow itself, right? I mean, C was designed in an era where computers were really slow.
Right, the 70s.
Yeah, so compilation had to be done offline, these big batches. You just couldn't afford to interpret code on the fly back then.
It would take too much processing power.
Exactly. So that historical necessity created this detached assembly line workflow. The commentators in our source, Jack and Jill, they refer to C as the deer in the headlights for this exact reason.
It was just standing in the road.
Its workflow was practically begging to be industrialized. The corporate mandate in tech has always been like, if a task can be batched, it can be automated.
Right, so the AI takes over the C code. It generates thousands of lines of boilerplate driver code in seconds, saving companies millions.
Yep.
But here is where the AI truck actually stalls. Here is where the model breaks down.
The physical wall.
Yes, the physical wall. Despite the LLM having this, planet-sized brain for writing code, it utterly fails the moment the software has to actually touch a physical chip.
This is such an important distinction. It's the boundary between digital theory and physical entropy.
Explain that for someone who might be new to hardware development. How is it different from writing a web app?
Sure. So software that lives in a cloud environment, like a web backend or a database, it operates in a mathematically perfect vacuum.
A 1 is always a 1.
Exactly. A 1 is a 1 and a 0 is a 0. It's pure logic. But embedded hardware is governed by the actual messy laws of physics.
Real physical boards.
Real boards, real crystals, real oscillators. You are dealing with things like parasitic capacitance on the printed circuit board.
Like stray electrical charges.
Yeah, exactly. Or you have electromagnetic interference from a nearby switching power supply.
So it's noisy.
Very noisy. You have oscillators that literally drift off their timing based on the ambient temperature of the room.
Wait, really? Just the temperature of the room can change how the code runs.
Oh, absolutely. If the room gets hot, the clock drifts. The physical world is just noisy, analog, and totally chaotic.
Okay, but let me push back on that for a second. Because someone listening might say, sure, hardware is noisy, but AI can process vast amounts of data, right?
Sure, it can.
And we have tools like logic analyzers and oscilloscopes that capture that physical noise and turn it into digital data.
We do.
So why can't we just, pipe a CSV file of the logic analyzer dump directly into the LLM and just let it figure out the timing issue? If it's so smart.
That's a great question, but the problem is that a logic analyzer dump is a snapshot of symptoms, not the root cause. If you feed an LLM 1,000,000 data points showing, say, a voltage droop on an I2C bus, the LLM will try to solve it mathematically.
Because that's all it knows how to do.
Right. It might suggest changing the pull-up resistor values in the code configuration or altering the clock speed.
Which sounds logical.
Sounds logical in a vacuum. But what the LLM cannot see is that the human engineer accidentally routed that I2C trace directly underneath a noisy motor driver on the physical PCB.
Oh, wow. So it completely lacks the spatial physical context.
Exactly. It has no eyes on the silicon, and this completely shatters the AI's context window.
Break down what you mean by context window there.
So an LLM relies on an unbroken chain of logic within its working memory, its context window, to maintain a flow state.
It needs to track step A to step B to step C.
Right. But embedded debugging is inherently disjointed. Think about the steps. Writing the C code, compiling it, flashing the chip, waiting for the failure,
which take time.
then hooking up physical probes with your actual hands, reading the logic analyzer on a different screen, and then trying to map those physical electrical bounces back to a specific line of C code.
It's all over the place.
It creates massive cognitive gaps. Now, when a human does this, they bridge those gaps with physical intuition.
Like, oh, the board feels hot, or I remember routing that trace weirdly.
Yes. But when an AI tries to do it, it loses the thread. It hallucinates fixes that make logical sense in a digital vacuum, but are physically impossible or just completely unhelpful on the actual board.
So the digital guess of what should happen violently collides with the physical reality of what does happen.
Violently collides. I like that.
And because the batch compilation loop of C is so slow and detached, the AI just can't iterate fast enough or accurately enough to cross that gap.
It's brilliant in the cloud, but brittle in the mud of the real world.
Which brings us to the hero of our story. Forth.
Yes. Fourth?
It has been in the background for 40 years. Like, never highly commercialized, never sold in a shrink-wrapped box at Best Buy.
No massive marketing budgets?
Right. Just quietly used by hardware engineers because it is tiny, it's fast, and most importantly, it is live.
It approaches the problem of computation from a completely different paradigm than C.
Where did it even come from?
Well, it was developed in the early 1970s by a guy named Charles Moore, and he built it specifically to control radio telescopes.
Radio telescopes. That's amazing.
Yes. And the thing was, he didn't have time for the compile flash debug cycle.
You couldn't wait around for batches.
Right, he needed to move the telescope now. He was tracking stars, so he built a system that didn't separate the drafting table from the construction site.
Okay, let's really break down the mechanism of how Forth actually works, because this is the core of why it resists AI automation.
It's all about the interaction.
Right, so unlike C, which relies on this massive external compiler sitting on your desktop computer, Forth is entirely self-contained.
It's tiny.
It is essentially a tiny live dictionary of commands. And they call these commands words, right?
Yep, they just call them words.
And this dictionary lives directly on the microcontroller itself. It operates using a stack-based architecture.
And because the compiler and the interpreter literally live on the metal, the workflow is fundamentally interactive.
It's not batch.
Not at all. With Forth, you don't compile a whole program and pray that it works. You open a serial terminal connected to the hardware, and you just type a single word.
Give me an example.
Let's say you type a command to toggle an LED.
Okay.
The microcontroller executes that word the very millisecond you hit return.
You see the physical result instantly in real time.
Instantly.
Going back to our building analogy,
Yeah.
if C is drafting a blueprint and waiting weeks for the construction crew to tell you it failed, Forth is like walking onto the job site with a tool belt, physically moving a door frame yourself, and instantly checking to see if the couch fits through it.
That's a perfect way to put it.
And if it doesn't fit, you just move the frame an inch to the left right then and there. It is a continuous, unbroken feedback loop.
Jack and Jill, in our source material, they term this the human in the loop philosophy.
I love that phrase, human in the loop.
It's so accurate because Forth is not a batch job to be handed off to a machine. It is a live conversation with the silicon.
A conversation.
Yes, you probe a register and the hardware responds. You adjust a value and the hardware reacts.
So the human actually has to be present.
Exactly.
Right.
This workflow cannot be handed off to an LLM in a cloud server because it requires real-time, synchronous interaction with physical reality.
Here's where it gets really interesting, though. Think about the overseas letter analogy for C.
Yeah.
If C is sending a letter overseas, Forth is like sitting in a room with a translator having a real-time back-and-forth conversation.
You can pivot instantly based on their reaction.
Exactly. And I want to ask you, the listener, to think about your own workflow for a second. Think about your daily job. How much of your job relies on real-time feedback versus batch processing?
That's a great point.
Because when you realize how much faster you learn when you get instant feedback, this hardware concept becomes universally relatable.
We all work better with immediate feedback, and for the embedded engineer, they have to be sitting at the workbench. They have to be looking at the oscilloscope, feeling the heat of the voltage regulator with their finger, and then feeding that physical intuition back into the terminal.
It forces you to be a participant rather than like an absentee manager.
Exactly.
But this creates a really interesting tension because we have this incredible AI that is an absolute master of pattern recognition.
It's read every data sheet ever written.
Right. And we have Forth, which provides this live conversational interface to the messy hardware. So how do we get them to talk to each other without breaking that live flow state?
How do we bridge the gap?
Yeah. And our source highlights a specific tool that does exactly this. It's called Regmon.
Short for register monitor.
Right. So explain Regmon for us.
So to understand Regmon, you have to understand how microcontrollers process data at the lowest level,
Okay, down to the metal.
down to the bare metal. At that level, hardware is controlled by registers. These are tiny, tiny memory locations physically etched into the silicon.
Real physical switches, basically.
Basically, if you want to turn on a timer, you write a specific hexadecimal value to that timer's control register.
Okay, fair.
Regmon is a lightweight tool that runs alongside Forth, and its sole job is to constantly pull these physical registers over the hardware debug wire, typically a JTAG or SWD interface.
So it's basically listening to the heartbeat of the chip.
Yes, it reads them and reports their exact state in real time.
Oh, wow. So this is the missing link.
It really is.
Because earlier, we established that the AI is blind to the physical world right away. It can only guess what the hardware is doing.
It's blind and guessing.
But with Regmon, we can pipe the live physical ground truth of the silicon directly into the LLM's context window as it happens.
It radically changes the dynamic.
Wow.
It really does. Let's trace a real-world debugging session to see this in action because it's super cool.
Yeah, paint a picture for us.
Okay, picture an embedded engineer sitting at their desk. They are trying to bring up a complex memory controller on a custom board.
Lots of things could go wrong.
Hundreds of things. So the human types a fourth word to initialize the clock tray.
Huh?
The physical chip executes it live right then. Instantly, Regmon reads the physical hardware registers and sees that the PLL, the phase-locked loop, failed to stabilize.
It just didn't lock.
Right, so it throws a hardware fault flag.
And normally, what would the engineer do?
Normally, the engineer would sigh, open a 900-page PDF datasheet, and spend 2 hours trying to figure out what that specific fault flag means.
Which is soul-crushing.
It is. But instead, Regmon feeds that physical register state directly to the LLM.
In real time.
In real time. And the LLM, which has ingested every single datasheet on the planet, instantly recognizes the pattern.
Oh, that's amazing.
It sees the fault flag, cross-references it with the microcontroller's specific architecture, and suggests to the engineer, hey, the PLL didn't lock because the input voltage dropped when the peripheral activated. Try typing this fourth word to increase the wait state before initializing.
Wow. So the AI isn't replacing the human.
Not at all.
It is acting as a high-speed technical co-pilot.
Exactly. The human evaluates the suggestion, types the word, the chip reacts, Regmon reads the new register state, and the loop continues.
It's a live pairing.
It's a dance. The AI handles the encyclopedic pattern matching of the documentation, which it's great at, and the human handles the physical intuition, the spatial awareness of the board, and the live conversational flow with the hardware.
This is wild because it fundamentally changes the daily life of an embedded engineer.
It totally shifts the dynamic.
It shifts it from a factory replacing a worker to, like you said, a pilot and co-pilot flying a plane together.
If we connect this to the bigger picture, this fundamentally rewrites the economics of software engineering.
How so?
Think about it. For decades, the tech industry optimized for scale and abstraction.
Right. Hide the complicated stuff.
Yes. We built massive frameworks and ecosystems to abstract the hardware away so that millions of developers could write code without ever needing to know how a processor actually works.
You didn't need to know what a register was.
Exactly. And that created a massive, highly paid workforce doing essentially procedural, batch-processed work.
Which is exactly what the AI truck is currently flattening.
Precisely. The ecosystems that were built for scale, the massive C libraries, the NPM packages, the bloated pip dependencies, those are the easiest targets for automation.
Because they're just text in, text out.
Yep. But Forth never scaled like that. It remained obscure. It never had a shrink-wrapped commercial ecosystem.
It was almost like a secret club.
It was a niche tool used by engineers who actively needed to speak directly to the metal.
Jack and Jill make a brilliant point about this in the source, but the economics of rarity here.
Oh, yeah, the professional moat.
Yes. They point out this profound irony that Forth's historical weakness, its obscurity, and its lack of massive corporate adoption has actually become its ultimate professional moat.
It's so ironic.
There is no huge, bloated, sprawling, industrial-scale Forth workforce for a corporation to just automate away.
You can't fire a team of thousands of Forth devs because they don't exist?
Exactly. The engineers who use it aren't just typists. They are hardware whisperers.
And that is where long-term career stability lies in this automated industry. The roles that survive this automation wave won't be defined by how fast someone can write boilerplate syntax.
Because the AI can do it faster.
The syntax is literally free now. The AI writes it instantly.
So where's the value?
The enduring value lies in specialized physical knowledge. The engineer of the future must understand the silicon.
You have to know what's happening on the board.
They must understand ground loops, timing constraints, memory architectures. They must be able to maintain that live conversational flow state with complex physical systems.
So wait, I want to make sure we ground this reality for the listeners, though.
Sure.
Because someone listening might be thinking, okay, does this mean every embedded C developer needs to panic, delete all their repositories, and spend the next 6 months mastering a 40-year-old stack-based language?
Right. Should everyone learn Forth today?
Yeah, is Forth going to replace C as the mainstream industry standard?
Realistically, no.
Okay, phew.
I mean, that was never its purpose. There are billions of lines of legacy C code running critical infrastructure globally.
Like power grids and airplanes.
Right. You can't just rewrite the firmware of a commercial airliner in Forth overnight. C will definitely remain, but the nature of the C developer's job will contract.
The junior roles, you mean?
Yeah. You will need far fewer junior developers grinding out basic driver code, and a much higher concentration of senior engineers who can step in and debug the physical interface when the AI's generated C code inevitably crashes the board.
So the human expertise is more valuable than ever, but it's a different kind of expertise.
Exactly. It's hardware expertise.
But the twist here, and I love this part, is that AI is actually breathing new life into Forth.
It really is. It's accelerating the niche.
Because the biggest barrier to entry for Forth was always this brutal learning curve.
Oh, it was notoriously hard to get into.
And it lacked modern tooling. Because it was so niche, it didn't have the sophisticated syntax highlighting, or the code completion, or the vast libraries that, Python or JavaScript developers just take for granted.
It was very bare bones. But an LLM doesn't care about the size of the community.
It knows everything anyway.
Right. It understands Forth perfectly well. And this means developers can use AI to instantly generate the scaffolding and the basic tooling that the thin Forth ecosystem always lacked.
Oh, that's so smart.
The AI actually lowers the barrier to entry. It solves the tooling problem, allowing a curious new engineer to bypass all that arcane setup process and jump straight into the live interaction with the hardware.
It democratizes access to it.
It really does. It invites curious developers into the fold.
It creates this fascinating synergy where the AI builds the tools that make the human better at interrogating the hardware, which in turn generates better physical data to feed back into the AI.
It's a closed, mutually beneficial loop.
Jack and Jill referred to this frontier in the transcript as AI-TroubleCity.
AI-TroubleCity is...
Which is just a great term. It is this misty, undefined territory where the pristine mathematical logic of the planet-sized AI brain crashes violently into the messy reality of the soldering iron.
And the engineers who operate in this space, they aren't looking to abstract the hardware away.
They want to get closer to it.
They want to speak directly to the metal. The legacy batch compile languages won't die overnight, but their roles will shrink, and Forth will simply become more visible as the ultimate power tool for this.
Murmurs in the mist. I just love that poetic phrasing from the source.
It's very evocative.
It is. For 40 years, these Forth developers have been the quiet ones in the background. They never advertised, they ignored the mainstream trends, they just maintained their live connection to the metal.
Just quietly working away.
And it turns out the quietest, most obscure language of all was the one best equipped to handle the AI collision.
It serves as a profound lesson in systems design, really. We often assume that progress always means moving further away from the physical layer, right?
More abstraction.
Yeah, more abstraction, more automation, more distance between the human and the machine. But Forth proves that sometimes resilience is found by stripping away the abstraction and insisting on direct, unmediated conversation.
It forces us to entirely reevaluate what we actually value in software engineering.
Because the code itself is cheap now.
Right. When the boilerplate code becomes a cheap commodity, the premium shifts to the context, the physical intuition, and the human ability to diagnose reality when the math fails. So, to summarize what we've explored today, we've looked at how an obscure, highly interactive language created the perfect bridge for humans and AI to co-pilot hardware development.
By rejecting that traditional batch cycle.
Yes, by rejecting the automatable batch compilation cycle in favor of a live, real-time conversation with the chip, Fourth turned its own obscurity into a literal blueprint for future job security.
It proves that specialized human expertise, especially when it connects digital logic to the physical real world, remains an absolute necessity.
It truly does. And as we wrap up this deep dive, I want to leave you, the listener, with one final, unmentioned, provocative thought to mull over.
Ooh, all right, what is it?
Well, we've spent this entire time dissecting how AI and humans are learning to converse seamlessly with rigid, fixed hardware through interactive languages like Forth.
Right.
We are adapting our software to talk to the chip in real time. But if this live, real-time pairing is so highly effective, how long until the hardware itself begins to adapt?
Oh, wow.
Right, I'm thinking about things like FPGAs, field programmable gate arrays.
The chips that can rewire themselves.
Exactly, chips that can physically rewire their own internal logic gates on the fly. Will the next frontier be dynamically shifting silicon?
That is a wild thought.
Imagine a scenario where the physical architecture of the processor actually alters its state in real time, actively mutating based on the live conversation happening between the human, the AI, and the metal.
Mind-blowing.
If our software has become conversational, maybe tomorrow's physical hardware will be too.
I love that.
Something to think about. Keep digging, stay curious, and we'll catch you on the next deep dive.